Greetings! I'd like to present our vision of digital twins for optimization of Industry 5.0 smart manufacturing facilities, which may allow to leverage both high level of digitization and human-centered approach. One characteristic feature of digital twins, which are virtual code representations of physical elements of the production line, is the high connectivity of production equipment units. Digital twins make use of Internet of Things sensors to monitor production lines in real time and may be the driving force and an enabler for smart and sustainable manufacturing. A food packaging enterprise has been selected as a test bed for this research. The factory already possesses a good level of digitization, with energy consumption data, quality checks data, and raw material usage data available for analysis. However, there is no implemented decision-making system supporting fast response of human operators to fluctuating market conditions and focused on reducing the energy consumption and raw material use optimization. The components of smart manufacturing line can provide a variety of data. The digital twin platform can process data on-site or broadcast this to cloud service to support decision-making based on mathematical models characterizing resource consumption and output quantity and quality. To determine the most efficient and feasible solution, several production regimes can be simulated using the digital twin in order to predict potential problems and optimize the manufacturing processes. The digital twin can also trigger edge system controls in case of malfunctions. For a specific processing stage, a set of parameters is to be prioritized in order to have sufficient amount of relevant information. By implementing a digital twin, it is possible to ensure real-time monitoring and analysis of manufacturing facility performance and energy consumption based on consistent and accurate data obtained from sensors to optimize processes for a more sustainable life cycle. The optimization diagram shows in this figure illustrates a general approach that can help solve the optimization problem. The inputs X and the outputs Y are qualitative and quantitative characteristics of the material and information flows that are production system that received by production system from external entities and sent to same or different external entities. The optimal control signal U** is a solution to an optimization problem to achieve the goals of particular smart manufacturing use case. The general optimization problem involves functional relationships of various types for a wide range of variables, making it difficult to solve. The optimization recipe can be created as a superposition of partial solution for different subsystems, and the equation describes specific processes only contain variables of that subsystem. Additionally, this strategy significantly lowers the optimization engine's processing power needs. Process state vector X and the control vector U are tuned with measured perturbations to refine the model. For the optimization, we constructed Lagrange polynomial which contains variables and controls parameters. In a general case, the fine optimization result is quite difficult to obtain. However, it is equation for each subsystem contains only the variables for this subsystem that the composition of the problem is quite straightforward, and the overall control vector can be constructed as the cross product of partial control vectors for all individual subsystems. The decomposition allows to tackle problems of lower dimensionality, either ignoring mutual influences or taking those into account as perturbations. Hierarchical approaches to optimization problems may be applied for optimal control of quasi-static processes. The hierarchical optimization is performed as a sequence of steps described here. The coordination procedure is the most effectively used for the model in which the number of relevant variables is greatly reduced by choosing only the most important ones for a defined goal of the manufacturing transformation, for example, energy consumption and the recycling rate. Using production data from the pilot food packaging facility, the solution of the partial problem for the most energy consuming and quality critical part, which was the forming press for that facility, has been attempted to test the proposed methodology. This allowed to identify the optimal regime for a particular production line. Numerical results show that the decomposition allows to drastically reduce the problem dimensionality, thus reducing requirements for the processing power of edge device which would be able to perform the needed calculations. This way the partial optimization problems with short time cycle can be assigned to the low resource edge devices which receive streaming data on product fast quality checks, and only if optimization of long term regimes of the production lines will be escalated to the high performance processing units, say cloud infrastructure, which will also reduce the informational security risk. The final slide summarizes our conclusions. Thank you very much for your attention.